Hello, this is the IC Engine's progress presentation, and the team members are Eric, Brandon, Samuel, and Claudia. Project introduction. Generative Energy Systems has built a generator that is based on a modular four-stroke internal combustion engine. For our purposes, it will be operated with compressed air, and the motor has two functions. One, it drives the engine when it is starting up, and two, it is driven by the engine to generate energy. The objectives: model and optimize the internal combustion engine, determine system parameters, and control for the new systems. And on the bottom is the overarching work kinetic energy equation that will be used to model the engine's work output. Here are some assumptions that will be looked more in depth later on. Progress. On the left are the completed things that will be going more in depth into this presentation, and on the right are the things that are left to do, which include adding air injection into our model and calculating the final work error. Methods and data collection. Starting on the right, you can see the engine, which has flywheels and is connected to the motor. On the side of the motor, we have the sensors, mainly a directly coupled encoder, which measures the angular position, and the force transducer, which measures the torque. Method: isolate the parts of the engine that produce work to create a model of the engine. As for our data collection, we will be collecting angular position and torque for the assumptions head off, no pressure, head on, no pressure, head on, pressure injection, for a variety of rest and steady state, different speeds, and with and without flywheel.
The torque transducer was calibrated for each week of data collection. Assumptions included that the torque equation would be linear, have an offset of zero voltage at zero torque, and that the equation would follow the format of torque applied equals the force times the radius of the lever arm. The transducer was calibrated using 5 different weight measurements. A York regression was used to find the gain for torque from voltage. An offset for torque and voltage was found when no mass was applied to the torque sensor. The equations for torque calibration are shown below. The work done by the motor was measured with the head off, so the assumption could be made that there was no pressure on the piston. Another assumption was that the coefficient of friction on the bearings on the crankshaft would remain constant at a steady state speed. Work from friction, work from air, work of the piston, and air work could also be considered as negligible when calculating work of the motor. The angular position and torque of the motor were recorded for 3 speeds at steady state and for acceleration from 0 to steady state with and without the flywheels attached. Work of the motor is calculated by integrating torque values averaged in 10-degree indices over the entire angular displacement of the motor in each trial. Piston position relative to time and angular position were also calculated. The table on the right shows the values for work of the motor done for the first 2 weeks for each trial, including the head-on assumption for steady-state speeds with and without the flywheels. The main conclusions from calculating motor work is that the motor work is greater when the head-on assumption is made as opposed to the head-off assumption. Work of the motor also increases with less flywheels attached to the motor. Finally, the work done by the motor also increases as the angular velocity of the motor is increased over the same time period that data is recorded for. Work done by friction, friction torque, and work of the piston are found with the assumption of no head and no pressure. Work of the motor is opposite and equal to friction work in this case. Once again, the coefficient of friction is assumed to remain constant at steady-state speeds, and work of the piston can be considered negligible. Angular position and torque at steady state with the flywheel is measured at 3 different rotational speeds. The work of friction is found by integrating average torque values over 10-degree indices with the angular displacement of the motor. Friction torque is found by dividing motor work by total angular displacement. It was found that friction torque increases with an increase in rotational speed. Values for torque of friction can be found on the bottom right table. For finding the inertia of the flywheels, work from air, piston, and air can be considered negligible. Another assumption is that the angular velocity at the start of the steady-state portion of the motor running is equal to the angular velocity at the end of the steady-state portion. To find inertia, the motor would start from rest until it reached steady-state velocity and stayed there. Friction torque remains constant, but there is a difference in the work done by the motor and the work done by the friction as shown in the plot. Average torque is integrated over the angular displacement to find motor work. Friction torque is found in the steady-state portion of the torque plot and integrated over the total angular displacement to find friction work. Inertia is found using the equation in the top right using motor work, friction work, angular displacement, and angular velocity. The values for experimental inertia of the system with and without the flywheel plates is shown in the top table. The values for theoretical inertia of the system was calculated using the L05 theoretical equation for 4 plates and 1 plate, and are shown in the bottom table. We found that the inertia of the flywheel system would increase as more mass plates were attached to the system. The experimental value of inertia of the 4-plate flywheel, 0.0135 kilogram-meters squared, will be used in future calculations and models. This experimental value has a 36% error with a theoretical value of 4 plates.
Calculating the work done by the air in the system is another important consideration. As the intake valve is open during the intake stroke and the exhaust valve during the exhaust stroke, there is negligible work done during these phases. For the first week of the experiment, the engine head was removed, which made the work done by the air negligible as well, as the system is open to the atmosphere. With week 2, the engine head is attached, but no external air is introduced into the system. This means the system is modeled by work done by adiabatic compression. To find this value, the measured dimensions of the engine and the atmospheric pressure conditions are incorporated into the equation shown below. This produced a work output of negative 25.261 joules of work done by the air. For the experimental data, work error and work done by the piston are assumed to be zero. The work done by friction and the work done by the motor will be combined with the energy of the flywheel, seen in the equation on the left, to find the work done by the air in the engine. For week 3 of the experiment, external air will be injected into the engine cylinder. This will adjust the assumption of the adiabatic expansion used for analysis here. Without injected external air, the work done by the air in the power stroke is assumed to be equal to opposite of the work done by the air in the compression stroke. This means the work done by the air in the power stroke is equal to 25.261 joules. For the third week of the experiment, work will be done by the external air that is injected into the engine cylinder. This value will be found experimentally through evaluation of the equation on the left of the figure seen below, incorporating the inertia of the flywheel, angular velocity of the flywheel, work done by the motor, and work done by friction. For the model, a combination of adiabatic and isobaric compression will model the compression stroke, and adiabatic and isobaric expansion for the power stroke. The difference between the work done during the actual experiment and the modeled system will represent the total error of the work done.
For the combined uncertainty calculations of average torque, encoder angular displacement, and motor work, assumptions were made including the averaging across the steady-state 10-degree incremented region for the accuracy and precision torque uncertainties, as well as the encoder count accuracy uncertainty was assumed negligible. The resolutions, precisions, and accuracy uncertainties were recorded for the encoder, force transducer, caliper, and mass scale. In order to solve for these desired system uncertainties through error propagation analysis for both the accuracy uncertainty of the torque seen in the top right equation and the motor work EPA seen in the bottom right. The following results were concluded from the uncertainty calculations. For average torque uncertainty, both the flywheel and engine head exhibit a greater influence on the system and therefore uncertainty. The encoder displacement uncertainty was constant across all trials, exhibiting its independence as a variable. For the motor work uncertainty, 3 of the same conclusions were drawn as for the motor work itself, including the increase with head, flywheel, and speed. The following overall conclusions have been drawn from a work energy model and experiments, all but including the injected pressure case. Motor work increases with the head-on assumption, flywheel, and speed, although yielding a greater uncertainty. And friction torque increases with motor speed, signifying the increased load on the force transducer needed to stabilize the system by providing this reaction force. Some system recommendations that can be made include modeling each work term for each stroke to improve accuracy of analysis, using data from the same motor and with better calibration sensors, and reworking the flywheel inertia to include a more accurate theoretical prediction and experimental calculation based on trials, including more flywheel speed and engine setup cases. The next steps with experimentation, data analysis, and reporting include adding pressure injection for the engine to drive the motor, finding where this occurs based on encoder and motor work data in order to optimize the engine work's output. Then with this final experimental case, the work engine model can be updated and validated with a calculated work error in order to determine the usefulness and reasonability of our sensors and system. Thank you.